I understood. My usual suspect with whom I'm working is Philippe Martins, and there are two others PhD students who are involved in this work, Hamza Adwat and Aurélien Vasseur. So if you, it's a pretty old stuff here when you were interested in teletraffic. That means the traffic for the plain old telephone system. You see that the mean number of simultaneous calls is varying along the day. So that means that you need to dimension the resources according to this traffic. And how do you handle that? The guys of teletraffic long ago found the way. They defined the concept of busy hour. You look at the hour where you have the most important traffic, and you made your computation for with this traffic. So you have a maximum traffic. So of course it works well, but you have some sort of waste of resources. But that's just to say, because for fixed telephone system, you have a number of resources which is fixed, so you can't do anything adaptive. So that's for time heterogeneity. Now, what about spatial heterogeneity? So you all know that when we make models of base station in a network, since the work of François and Bartek, that we use homogeneous Poisson point process. So if you look at this is the position, the points you see in this picture represents the base station in Palaiseau, the city just around here, and you see you have some sort of homogeneity. There is we don't see any hole or any cluster whatsoever. It's more or less homogeneous. So it's admissible to say, okay, we model that as a Poisson point process. So for those who don't remember what it is, that means that in a fixed domain, you have the number of base station follows the Poisson distribution of parameter, the intensity lambda times the area of the domain. And if you know the number of points in the domain, the locations are uniformly distributed. So this is the basic configuration with which we did a lot of work. Okay, but now if you look closer, so these are the points of the base station in a district of Paris. I don't remember which one. It's for all operators, all frequency band on the left, and all systems, 2G, 3G, 4G, whatever. And on the right, we extracted the locations of one operator and in one frequency band. And you see the difference between the two is that we don't have, you seem to have points which are, which avoid each other. There's some sort of repulsion in the cloud of points. This is done for engineering reason, just because when two base stations operate in the same frequency band, they generate interference. So you don't want them to be too close. So for you spread them according to some pattern. And you don't have clusters like you have here. See, you have very close base station. So if you look at the picture on the left, it's admissible that you can consider this as a realization of a Poisson configuration, of a Poisson point process. On the right, it's not feasible. So that means that if you are interested in this, in the picture on the right, you need to have some other model. So what's the difficulty in finding the good model. That is to say, you want a point process with repulsivity. So you have matter core, you have a lot of point processes which could be used. So when you make some models, you are taken between two fires. First, you want to stick to the reality, and second, you want to have tractability. So what does that mean? Reality, that means you want to capture a certain amount of features of your networks you estimate which are important. It's different from the approach from machine learning, in which you put every data you have and you hope that the system, the machine learning algorithm will tell you what's important and what is not. What is tractability? Tractability can be understood as you have a closed mathematical formula, or you have something which can be easily simulated. So both definitions are admissible. So the thing is, when you have a nice model with the features you want, which represents the features you have selected, you have explainability. You know that in AI algorithm, one of the biggest challenge is explainable AI. Because if you put everything in the algorithm, you don't know why it gives you this.
Specialized in.
If you have if you already choose your variable, it's easier. And then tractability, of course, you see where I'm going. Math formulas are more robust in the sense that if you change a parameter, you don't have to begin again all the computations in simulation. The slight change of parameter implies that you have to rerun the whole algorithm, and it may take time. Okay, so what kind of point process we can use to model repulsivity? There is a class I like pretty much, which is called determinantal point processes. So it's a masked by thing. So it's DPP. Why is it determinantal point process? It's constructed as this. You are given lambda 1, lambda 2, lambda n, which are positive and less than 1. You expect nothing here, and you consider Bernoulli random variable of parameter lambda n. Say you have ordered them from the highest to the smallest. Then you have also the choice of phi n, which is an orthonormal basis of n2 of some measure mu. You can change the measure if you want. And then you draw your Bernoulli random variable, and you look at the site, the set, In, which corresponds to the Bernoulli which are active, the Bernoulli which are equal to 1. Okay, you have Bernoulli which are at 0 and the other are equal to 1. And given that if you are in In, that means you have n. If the cardinal of In is equal to k, that means you have k particles, and the position of these particles as density, which is given by the determinant of this matrix. Okay, so there is a determinant, hence the name of determinantal point process. So it's look barbaric, but actually it has, since you have a very strong algebraic structure behind this, you have a lot of properties. So what kind of properties do you have? But this is a picture of, on one example. And if you don't have clusters points, or you have a lot of points in the circle here, and if you look closer, you see you won't have this kind of cluster you have in the Poisson point process. So what are the properties which are interesting? First, we know what is the Laplace transform of a DPP. The Laplace transform, you know, is expectation of exponential minus sum of f of Tn over Tn in the realization of a DPP. The Palm measure
adjustment networks.
A DPP is a DPP. You know, you just have to change the lambda i's and the phi i's, but it's a DPP. When you make the thinning of a DPP, you get a DPP. When you rescale a DPP, you get a DPP. That means it's what is thinning? Thinning is you have particles and you keep them independently from the other. You keep each one independently from the other with probability P. That means that you have a whole set of users, which is represented by your point process. And then you say, okay, I want to know, to represent the people, the users which are active. And if you say, okay, with probability P, each user is active, the resulting process of active users is the thinning of your initial process. So it's very important that the thinning of your process is still of the same class. Okay. So, and more than that, you have a very, very nice algorithm to simulate
easier to
this kind of processes. And it's one of the nicest algorithm I know, really. And you have approximate of this algorithm, and you can compute the error you make by using the approximation instead of a true algorithm. That was one of our work. So the last point there, the last property they have is when you superpose two DPP, you don't get a DPP. That's one problem. But if you superpose n DPPs, and if you have thinned each of these DPPs by something, okay, so beta circle n is the beta thinning of n, and when the rescaling at square root of beta, so that means you multiply each point of the process by the square root of beta, it converges to a Poisson process. So what does mean this result? This result means that, okay, on the right,
and we also have a much.
I have a DPP, but for one frequency band. But if I superpose the DPPs for all frequency band, this is normal, but at the end, I retrieve a Poisson process. And you even know that the convergence is at the rate 1 over n. That means the more you superpose, the closer you are to the Poisson process. Now, if you change your point of view, I told you that the I have to hurry up, I guess. Yeah. You have to we model users by a Poisson process. Now you want to take into account that they are on roads, that the mobiles, say cars, are on roads. They are not freely distributed in the whole space. So what are you doing? You are constructing a Poisson process of roads. Well, how do you do that? A road is identified by its angle with respect to the origin and its distance to the origin. That means it's a couple of a radius r and an angle theta. That means you construct a Poisson process on r times 0 pi, and that gives you the process of roads. And each of these points, so that means each of these roads, is marked with a Poisson process on the line. And these marks gives you the position of the cars on the road. So this is clearly a marked Poisson process. And it was studied in the paper by François and Choi in 2018. And as such, there is a very, since it's you can see it as a transformation of a Mark-Poisson process. That means the superposition and the feeling of this kind of process is still of the same nature. Because when you superpose two Poisson processes, you get a Poisson process. When you fin a Poisson process, you get a Poisson process. And what you get also is if you have, if you let number of roads going to infinity and the number of mobiles per road going to 0, then the global number of cars goes to a Poisson process of intensity C. That's a very common properties of Mark point processes. And you can also benefit from the representation as a Mark Poisson process. You have some kind of thing that you have what is called the Poincaré inequality. You can estimate the variance of any function of your point process by this expression, which amounts to say what happens if I add one road with its number of cars. How does it modify F? Okay. Now you can go even closer. You can go indoor. That's the work of Philippe Martins and one of his and Catherine Dragon. This is crack stitch tessellation. That means you draw a line, and then each part of the you have two domains. Each domain is equipped with an exponential lifetime. At the end of the exponential, then you draw another line, either horizontal or vertical. And then you do the same thing. You iterate the same thing. At the end, you get something like this. This is a very nice model of the rooms inside the building. And then they here computed the wave propagation. You have here 1 emitter, and you have this is the points which are seen in line of sight, and here you have points in line of sight plus 1 rebound. So this is a huge simulator, very precise, with a lot of precision physically. Ray tracer, but they take into account the physics of the wave propagation. Okay, so once again, the first thing is to define a way to create random rooms, because the walls are the problem to the propagation. Okay, now another way. I told you that at the very beginning that we couldn't do anything else but considering the busy hour because the number of resources were fixed. But now imagine that your mobile networks is added by drones. Drones, you can put them wherever you want. And here you have the number of WiMAX antennas in Paris. And you see that you have some sites. And according to the sites, you have maybe you have one site with 20 WiMAX antennas, the other are 6, 2. So the mean number is 2.5. The variance is 11.6, and the kurtosis is 20. That means it's a very, very heavily, it's probably a very heavily tailed distribution. If you represent, that means the thing is, the number of WiMAX, station is correlated to the number of users, of course. So
the triangles of the mesh must be
to construct a point process with somehow clusters.
Always the case in a realistic machine.
Yeah. So if I want to construct a process with clusters, what are the interesting properties
1 year later
of the Poisson process? First, as I already told you, thinning and superposition of Poisson process is a Poisson process. And these two properties are equivalent actually to the form of the Laplace transform. So I want to construct a process which is for which I have these three properties. The solution is given by discrete alpha stable point processes. It was first introduced by Davidov, Molchanov, and Zuyev a while ago in a very, very beautiful paper. How does it work? You consider the Shibuya distribution. Shibuya distribution is a very funny distribution. It's a parameter alpha. The probability of x is equal to 1 is equal to alpha. And then the probability of x equal to 2 is 1 minus alpha times alpha over 2. It's like a geometric distribution, but each time you lose, the probability that you gain at the next step is divided by the number of steps. It's a very strange thing. And you get that the probability of x equal to k is given by this formula. And a Shibuya process, you are given a probability measure, and you construct a Shibuya number of independent points distributed according to mu. So this property, why Shibuya and not anything else? Because Shibuya has a very, very nice property. If you take a Poisson distribution and you make the thinning of the Poisson distribution, that means you take a Poissonian number of Bernoulli random variable. And you sum all these things, you get a Poisson distribution. If you do the same thing with Shibuya, you get a Shibuya distribution. And these are the only distribution for which you have this property. So that explains that you have this kind of identity. That means you take n prime and n prime prime, three copies of the same point process, independent, and you have the A thinning plus the B thinning of n prime prime as the same law as the C thinning of n, provided by M to the power alpha plus B to the power alpha equal to C to the power alpha. If you take alpha equal to 1, you retrieve the characterization of the Poisson process. If you have alpha between 0 and 1, you have d alpha s. And that explains that all the interesting properties I mentioned for the Poisson process, thinning, superposition, calculation of the Laplace transform do hold for the Shibuya point process. Okay, and then since you have at the very low level, you can construct this as the image of a Mark Poisson process. You have this theorem that a d alpha s tends to Poisson process as alpha goes to 1, and you can even precise the rate. It's 1 minus alpha. You have the point, and then you superpose some processes which are not all point processes. You have some
path between points is the
it converges to a d alpha s at rate
following
1 minus 1 myself. So
then once we have our geodesic.
So this is useful. Once you have that, you can say, okay, my mobiles are distributed according to a d alpha s. So my drones will follow the repartition of my of the mobiles. That's what we did with in the last communication paper. So I don't have time to speak about satellites, but it's again more or less the same thing. You want to draw. You want to say how satellites are.
Between any particle.
You take a direction on the unit sphere. You take the orthogonal plane to this direction. This gives you the orbit. And on the orbit, you put a Poisson process of satellites.
Geodesic.
When you do this, what you can
Some
find
is because it
is
is
that if n is large, and the number of orbits is large, and the number of satellites per orbit is small, the whole number of satellites converge to a Poisson process of uniform distribution of the sphere. And you can even precise the rate. That means if you look, there is one question which is interesting. You take a point on the whatever, on the Earth, and you look at the closest satellite. That means you look at the distance between X and the pi n, which is the process of satellites. And you look at the other way at the process, at the distance
the triangles
and the Poisson, uniform Poisson process. These two random variables are closed. Their law, the distance between their law is bounded by 1 and the distance between their expectation divided is bounded by 1 of. And you even have something called concentration the probability that the function of In is different from this expectation from a level X. So the original model was by Ocati, and essentially Ocati was the PhD thesis of Ocati. Then François and Choi again had another model, introduced this model with the choice of direction, and then you choose the orthogonal place and so on and so forth. And the convergence to a Poisson process is something we did with my PhD student. And that's all. I just finished it.
Thank you. So I would like to know a bit. I don't know anything about this kind of method, so and I'm very curious. So this might be a naive question. So when you present your models, different models, Poisson process or the other that is more repulsive, etc., you said that the repulsive model represents better the base stations of a operator, for instance. This is the thesis the hypothesis that you have. Now, in order to believe this hypothesis, either I can see it with my eyes, either I can agree with you because I see it with my eyes, but with my eyes I cannot see. I mean, for me, I don't know. Or I can believe you because of a dogma. Or is there any quantifiable empirical measure that can tell me, okay, this distribution matches better in every territories of France, or with the actual distribution of vehicles on the road or antennas, etc. I mean, how can one validate empirically the good match between the model, or that one model matches the reality better than another?
That's a very good question. Hard to answer. What we did in a previous work, you have some software when you are when you look at point processing in 2D, you have something which is called pair correlation. Okay, and you have a lot of functions. You have a function f, g, h, f, j, h, g, k, and so on and so forth. And it turns out that guys of statistics say one way to classify point processes is to compute the J function. And it turns out that for GPP, you can compute explicitly what should be the G function. So you can take your data and compute the parameters of the G function. That's the best you can. But we don't have tests on. You have some tests. If I have a value of point, if H0 is the hypothesis, this is the Poisson process. You have some tests that tells you yes or no. But you don't have tests to verify the for not. The best you can do is try to estimate.